Alright, let's go into lesson 4, inscribed angles. There's not a lot of new information in this section, and I think we did this in Algebra 2, so this shouldn't be that new. The first thing is our definition of an inscribed angle. The definition says an inscribed angle, we did a central angle in the last lesson, so it's a little bit different. An inscribed angle is an angle whose vertex is on a circle and each of whose sides intersect it in another plane. So this red angle here is an inscribed angle. Its vertex is on the circle and the other sides intersect the circle in two different points. So remember the central angle, it started here at the center and then it intersected the circle. So inscribed angle, a central angle would look like this one. So we have our circle, and if we had our center point, the point in the center, we would draw our central angle, would look like this. It comes into the center, and from the center out. So this would be an example of a central angle right here. So you can see the difference between them. This is inscribed, this is central. Theorem 72 says an inscribed angle is equal in measure to half its intersected arc. So here we have, I can't even read what I wrote there. Angle A is inscribed in circle O. Angle A is half of the measure of this arc. So for example, if the arc were, let's just say that this was 64 degrees, then the angle is half of that. So this angle right here would be 32 degrees. That's what that says. Measure of angle A equals half of the measure of arc BC. If you had a central angle, say you had this is a central angle, this is like 100 degrees, your central angle is exactly the same. So this would also be 100 degrees. The central angle is the same as the intersected arc. Inscribed angle is half of the intersected arc. And of course you go the other way around. If this was 32, then this would be double 64. Corollary 1 says inscribed angles that intercept the same arc of equal arcs are equal. So if I had another angle, let me just draw another angle in another color. If we had another angle that intercepted the same arc, that came down like this, and then it came out like this. See how this light green one is intersecting the same arc? So this angle would also be 32. That's just kind of common sense. Or if you had another arc that was 64, then these two angles would be equal. Corollary 2 says an angle inscribed in a semicircle is a right angle. So here I drew one. Just if this is a semicircle, the yellow part above the blue line here, we have an angle that hits right here, hits the semicircle. Well, that would make sense because you're intercepting. This would be 180 down here. This arc that it intersects, and so the angle would be half of that. So this would be 90. So an angle inscribed in a semicircle is a right angle because it's going to hit right at 180, and then this would be half. Okay, let's try a couple problems, and then I'm going to do two proofs. This is problems 20 to 24. They give you this picture right here, and they're going to give you that this angle is 37, and this angle is 54. The first question says find angle R. This is an easy one. This is a triangle. Triangles add up to degrees. Measures of the degrees of the triangles add up to 180. So I started out with 180, and I subtracted off the 54, and subtracted off the 37, and so we get the measure of angle R is 89. So this one is right here. If we want to just write it in, it's 89 for future reference. Number 21. I need to look in the book to see what that is. 21 says, is RD tangent to circle O? So here's RD. Is it tangent to circle O? Well, it looks tangent. It looks like it hits this point. It looks like it could be tangent. But you have to remember from the definition of our tangent, it has to form a right angle. It has to be perpendicular to the radius. And this is 89, not 90. So therefore, it's not a tangent. So remember that. It has to be perpendicular to the radius to be a tangent. So this is no, it's not a tangent. Tricky. It has to be perpendicular. Not perpendicular because it's not 90 degrees. And 22 says, is UGR a semicircle? So they want to know if UGR, the measure of UGR, and I just want to know if UGR is a semicircle. Let me look at that. I don't even see a G in this. UG, oops, G's up here. I don't have it in there. UGR. Is it a semicircle? What do you think? Well, we have a diameter, and it's dividing the circle in half. All diameters divide the circle in half. So UGR is a semicircle. So we would say a big fat yes for that one. Two more. Now we want to find the measure of arc RN. Well, here's RN. And here is an inscribed angle right here. It's intersecting the circle between R and N. So remember, according to our definition, an inscribed angle is equal to the measure of half its intersected arc. We can go the other way. The intersected arc is twice the angle. So we would double this, and we would get 74 degrees. This arc right here is double the inscribed angle, so it'd be 74 degrees. Hopefully this is all making sense. There's not a lot of new information here. And then finally we need the measure of UN, this arc right here. This is another one. If we have, this is a semicircle right here. If this one's 74, then this one's just going to be 180 minus 74, which I'm going to toss this into my calculator. 180 minus 74, and we should get 106. I could have done that in my head. 106. So these two together, this one is 106. Something doesn't quite look right, does it? 106 minus 74 is 180 minus 74 is 106. Let me just check the answer. It could be my picture. Yes, 106. That's my picture. Okay, let's try two proofs. We'll go through those fairly quickly, I hope. Hold on a second. Okay, so I'm going to do proof 34 first. The hard thing with the proofs is you have to remember theorems from the entire book. So feel free to look through your books. I think most of the theorems and definitions are in the back of your book if you need them. Okay, this one you have a circle, and we're given that LO is parallel to MA, and we're to prove that MA, I'll just mark what we're trying to prove in green. MA, measure of arc LM, where they get MA, is we're going to prove that it's equal to OA. So let's see if we can do that here. It looks like I have down, we're going to do this in 4 steps. So first thing we're dealing with, we want these two arcs to be equal. One thing we can do is we can say, if we have parallel lines, we can say that this angle is equal to this angle. So we can say the measure of angle LOM is equal to the measure of angle LOM-OMA. And the reason for that is fellow lines, what are these called? Good review for the final. These are alternate interior angles. So you could just say alternate interior angles are equal. Now we have these two angles are equal. If we have our, from this lesson, we have a corollary says inscribed angles that intercept the same arc or equal arcs are equal. So we can use that one. For step 3, we can say, oh, that's not how we're going to go about it. Okay, we're going to say angle. We can say angle, the measure of angle L, that's an O, OM equals half of LOM. LOM is half of arc LM. And we can say the measure of angle OMA equals half of arc OA. Okay, well, the reason we can say that is Theorem 72. It says an inscribed angle is equal in measure to half of its intersected arc. So I'm just going to put here Theorem 72. Remember, this is the angle is half of the intersected arc. So that's half of it. Now we can say, since these two are equal, then these two are going to be equal. So we can say half of, I guess we have 5 steps, arc LM equals half of arc OA. And these are the measure of. And the reason that we can do that is just substitution. And then finally, we can say the measure of arc LM equals the measure of arc OA. And the reason for that is we're just going to multiply both sides by 2, so we just say multiplication. So all I did here is I used the parallel lines to get equal angles. Then we can say the angles are equal to half of the arc. And then we can substitute and say the half arcs are equal, and then multiply both sides by 2. Okay, last proof. This is 36 in your book. So this one, we're given that AR equals RT. And I have those marked on there. And then they tell us all these things, EA, ER, AT, and AR and RT are chords. So obviously they're chords. Okay, let's see what we can do with this one. This one looks kind of tricky. We're to prove that AH over HT is equal to AE over ET. And the way that we have this proportion, it reminds me of chapter, I think it's chapter 10, where we did all the proportions for different things. So hopefully we'll be able to use one of those. So the first thing is I just wrote down the given. I didn't write them all down, but all those things are chords. And we're given that AR equals RT. Then we can use, if two chords of a circle are equal, their minor arcs are equal from the previous lesson. So here we have two chords are equal, so we can say that their minor arcs are equal, so that we can say the measure of AR equals the measure of RT. And I don't exactly remember what lesson that was. That was one of these lessons. Must have been lesson 1 is what I'm thinking here. Exactly. Okay, it must be lesson 1. Nope, I don't see it. I'm not sure what lesson it is, but it's true. So the reason for this is measure of, we can say if two chords of a circle are equal, their minor arcs are equal. If two chords equal, minor arcs equal. Hopefully you see that. Here's our chord. That means this. If these two are equal, then their minor arcs are equal. Okay, moving on. This proof's a little bit longer, so I'm going to go faster. So the next thing we can say is angle AER. We can say the measure of angle AER is equal to the measure of RET. AER is equal to the measure of RET. So this is in this lesson that says inscribed angles that intercept the same arc or equal arcs are equal. So we have that this arc is equal to this arc. So their angles, their inscribed angles are equal. So let me try to write that out. I would say inscribed angles that intercept equal arcs are equal. So I don't know how to shortcut this. Inscribed angles that intercept equal arcs are equal. A lot of things to keep in mind. So let me mark this in the picture. Now we have, here's our inscribed angle. Here's another inscribed angle. Their arcs are equal, so therefore these two angles are equal. Okay, hopefully we're getting somewhere. Now you can see that this ER bisects angle AET. So we can say on step 4, ER bisects angle AET. And the reason we can say this is because if a ray divides an angle into two equal angles, it bisects it. So if an angle is divided into two equal angles, it's bisected. Bisected. Hard to write on this thing. Sorry, it's just floppy. And finally, this is the hard part because this is from chapter 10. It says if an angle is bisected, then its parts form a ratio. So here, do you remember that from lesson 10? I don't have it written down exactly what theorem or postulate or whatever it is. But we can say AH over HT equals AE over ET. And AH over HT equals AE. And this proof is all dependent on how well you know the postulates and definitions. We haven't had postulates for a while. The corollaries, definitions, and theorems from the previous chapter. So you're going to have to go back and look at those every once in a while, especially as you start getting ready for the final. You're going to need to know all these inside and out. So this one says an angle bisector in a triangle divides opposite sides into segments that have the same ratio as the other two sides. So I'm not going to write that down. I'll start to. Angle bisectors divide opposite sides into segments that have same ratio. And I'm going to run out of room. Same ratio as other two sides. So hopefully that makes sense. The hard thing for this one is getting this ratio. You have to remember back to the other theorems and figure out how to put that into play. Alright, give those proofs a try. Remember, you just have to do the odd proofs and do all the problems in lesson 4.